Welcome back to this module, Data Level Parallelism Exploitation using SIMD Instruction Set Extension. I will now look at a case study, how the SIMD instructions can be used using SSE intrinsics. Here's a brief outline of this lesson. First, I will discuss how SIMD instructions can be used. Then I will give an overview of Intel's streaming SIMD extension and an example, and finally I will conclude. Remember the challenges and outlook I discussed a few lessons ago. The question was how to increase instruction level parallelism if the hardware and/or the software cannot find it. And the idea we had was to give at least part of the task back to the programmer so that the programmer should indicate where there is data level parallelism using SIMD instructions. And that's the main topic of this lesson. How can the programmer exploit and use the SIMD instructions? Basically, there are three approaches from extremely low level to high level. At the lowest level is the assembly level. Then the programmer, the developer, the application developer has to do everything. He has to vectorize the loop. He has to discover which loops are vectorizable. He has to allocate the registers. He has to take care of a register allocation. And he or she, of course, also has to perform instruction scheduling. The next level is, and the next idea is, let the compiler do the tasks it is extremely good at. Unfortunately, there are many reasons why a compiler thinks it cannot parallelize or vectorize a loop. Right? Because it cannot disambiguate different pointers. Do they point to the same memory area or not? Or there are many reasons actually. On the other hand, register allocation and instruction scheduling, at these tasks a compiler is very good at, much better actually than even expert human programmers. And the highest level is to say, let the compiler do everything. This is actually a big research topic for auto-vectorization compilers. Then the compiler has and to vectorize and to allocate the register and the instruction scheduling. But as I said before, there are many reasons why a compiler needs to make a conservative assumption and cannot automatically vectorize a loop and could use a little bit of help from the programmer there. This table here shows an overview of the SIMD extensions that have been added to the x86 instruction set architecture of Intel. It started a long time ago, 96, with the MMX extension, where the register file was shared with the floating point, where the number of registers was limited to 8, the register width was 64-bit, the number of operands were 2, and the supported instructions were floating point and integer instructions. Then came all the SSE extensions, and also AMD, which is a competitor of Intel, introduced its own SSE extension. And then Intel switched to advanced vector extensions, AVX and AVX2 very recently. There we have another register file, more registers. The other registers are kept for binary compatibility reasons, but also the register width has increased, and also Intel started supporting instructions with 3 operands. Let me now give a brief introduction to the intrinsics that you can use when using SSE instructions on Intel processors. For the first declaration here declares a 128-bit variable that will be mapped to one of the multimedia registers XMM. And furthermore, if you declare this data type, then the compiler will align it to a 16-byte boundary so that we can use aligned loads and stores, which are, since we know by the previous lesson, much faster than unaligned loads and stores. Then we have a load instruction illustrated here. We can use this. It looks like a function call, but it is actually translated to an SSE instruction, directly translated, which loads the 128-bit fixed point value or integer value from the address pointed to by P. And P must be 16-byte aligned. And it directly corresponds to a move double word, move quad aligned instruction. Then we also have a load unsigned instruction, which load unaligned instruction, which generates directly a move quad word unaligned instruction. And here we have a move store instruction, which also generates one instruction and one instruction only, a move quad word aligned instruction. Let's now look at an example using these intrinsics. Right? We're going to calculate this kernel, this very simple loop, for I equals 0, I less than 100, I plus plus. Output I becomes input I times input I, so the square of input I plus 3. The input is using this attribute aligned at a 16-byte boundary, and so is the output. Using SSE intrinsic, we can use this code. This code aligns, this code allocates the input and converts the pointer to something that points to this data type, and similarly for output. And we know that by default it aligns at a 16-byte boundary. We need this variable xmm0 as a temporary result, which is also aligned at a 16-byte boundary. And we use the constant value 0, add 3, which we translate, which we split into a vector consisting of the values 3, 3, 3, 3, and so on. Then we have a loop that loops 24 times. We load 4 times the input vector, invec. Then we square using the multiply low operation, all these 4 integers. And then we add in the third instruction the scalar 3 that we have splatted into a vector using the add 32 instruction. And finally, we store back the result to memory using the store signed integer 128 instruction. Here's another example. Vector multiplication and add using 8-bit values. Again, here's the simple C source code. We have a loop that loops from 0 to 100, and output I becomes the square of input I plus 3, and this is clipped to the maximum value using a table, which is a conventional trick in software to avoid branches when clipping. In fact, this is not an example, but this is an assignment to test yourself. Here we declare the input vector, the first statement. The second statement declares the output vector. Here we declare a temporary variable. Here we split the add vector, and then you are supposed to write your code here. Finally, a sample question. What is the main advantage of writing SIMD code using intrinsics rather than assembly code? And to summarize this module, basically there are three ways to exploit SIMD, either using inline assembly, which requires you to fully understand all the assembly instructions and is therefore very, very error prone and not recommended. The second possibility is to use intrinsics, which allows you to factorize all the code you can think of, which is allowed to factorize, of course, but also because the compiler has to be very conservative, whereas the developer knows if certain variables, certain pointers point to the same variable, therefore knows that the loop is parallel and can be factorized. And the third approach is using auto-vectorization. So basically, automatic vectorization and parallelization have been for many years the holy grail for high performance, but the state of affair is that the state of the art is that to achieve the highest performance, we still need intrinsics, which is even a level higher than assembly, but not much higher. Thank you for watching this video. This completes this module. Hope to see you back.